Hello. In this video, we're going to go over the mathematical model that I used for my three-stage amplifier, which gave me pretty accurate results. Before we get started, I'm going to recommend everybody to stop this video if you have not already watched the activity 3.4 frequency response of a CE amplifier. So if you haven't watched that video, go to Canvas and watch that video, because all of the formulas that you see in this first slide are all gone over in that video, so it's pretty important for this video. Okay, so the lower frequency response calculations, all we're really doing is taking the Thevenin resistance of the input and doing an RC frequency response for the capacitor. And then so we're going to be doing that for each capacitor in the circuit. You have your input, your output, and your bypass capacitor. So the issue is that we have multiple stages. And I'll pull up the circuit. So we have the input capacitor, output capacitor, bypass capacitor, and notice this bypass capacitor is not hooked up. So the second stage, this is the input capacitor, output capacitor, bypass capacitor, and then the third stage we have the input capacitor and the output capacitor. And so what you're going to want to do is calculate each one of these frequencies for the respective capacitor. And then you're going to take the root mean squared of all of the capacitors to give you a final result. And so I'll pull up my work. This is the lower frequency response. So for the input capacitor, I calculated 8 Hertz. For the output capacitor of the first stage, I calculated 5.28 Hertz. And then my schematic did not have a bypass capacitor, so I took the root mean squared of 8 Hertz and 5.28 Hertz, and it gave me 9.6 Hertz. And you're going to do that for each capacitor, or each stage, right? So input 25.5, 7.97, and then 40 Hertz, and then root mean squared, and you get 48.2. And then the coupling capacitor, we have 32 Hertz and 5.85 Hertz. We take the root mean squared, and we get 32.57. So going back to the formulas, that is what we're doing here to get the 9.6, 48.2, and 32.6. Once you have those values, you're going to take the overall result and take the root mean squared one more time, and that'll give you a really accurate result. And I got 58.97 Hertz. Going back to the work shown, you can see my calculated was 58.967, and that was taking the root mean squared of the results. So I did the root mean squared, had the result, root mean squared had the result, root mean squared got the result, and then took the root mean squared of all of those results, which gave me that 58.97. So let me pull up the schematic and we will do the AC analysis and get a Bode plot. So we're going to type a sweeps decade, number of points is 1,000. I like to use a start frequency of 1 Hertz and a stop frequency of 1 megahertz. And we'll run it. And our pass band, you'll notice, is 1.2, about 1.23 dBs. So our 3 dB down point will be 1.23 minus 3, which is negative 1.77. So we're going to take the cursor and move it to the left until we get to negative 1.77. And the result was 58.88 hertz, which is really, really close to 58.97 hertz. So I challenge anyone that watching this video to try these root mean squared version and just see if it is accurate for you as it was for me. I thought it was pretty cool. I'm always like trying to get really accurate, and I know the frequency response tends to be a little bit elusive because the parasitic capacitances and other frequency issues. But yeah, it was pretty accurate. So a couple things that I wanted to point out. For the formulas, when you're taking the first stage, for my first stage, I have a series resistor and we have the function generator. So in my formula that I used, I included the series resistor, and although the formula does not show the function generator, if you go to my work, my Excel sheet with my work, I call the function generator ZG, or the impedance of the generator, and it's 50 ohms. And then if you go to the lower frequency response, the input Thevenin resistance, I included that ZG right after I included the series resistance. So it's only 50 ohms, but for trying to get a really accurate result, it's important to include as much as you can. So that's one thing, series resistance. And then I wanted to go over why I didn't use this bypass capacitor. So originally, I only had one capacitor here that was 10 microfarads, and I was using one 10 microfarad capacitor here. So I had two swamped common emitters, and the reason I'm calling them swamped is because this resistor is makes it a swamped, because you're adding resistance to that diode resistor, or diode resistance. But anyways, I was using two 10 microfarad capacitors, and I'm going to run that real quick. This is the Bode plot. And the first thing that I notice is in the passband, my magnitude is extremely high. So that means that it increased the gain quite a bit. But so let's say our passband is 7.725 minus 3, so 3 dBs down will be 4.725. So take this to the left till you get to 4.725, 0.725-ish. And my frequency is above 100. And in the lab manual, it says that we need to have a frequency response of 100 hertz or less. And there's way too much gain. We need a gain of 100. This has way more gain than that. And I'll do a transient analysis just to see where we're at. So our transient analysis shows that we're getting about 4.65 volts peak to peak, and we should be getting about 2 volts peak to peak. So the bypass capacitors can definitely add gain because it's creating a short for your AC, and so it drops the AC signal through the bypass capacitor, which can increase the gain. So what I did is I just got rid of this bypass capacitor, so I'll just snip the wire so we can quickly see the result. And I tried running this, and let's do a transient analysis just to make sure we're back to about 2 volts peak to peak. Yeah, so 2.27 volts peak to peak, we're in the ballpark range. Now let's do a Bode plot. Okay, our passband is back to 1.23, so negative 1.77 should be our 3 dB down. And we'll notice that we're still above 100 Hertz. Okay? So you're looking at your circuit, you're like, okay, how do I get the frequency down? What do I need to do? If I mess around with these bypass capacitors anymore, is it going to affect my gain? So I'm going to pull up my calculations again, and I showed you the lower frequency response calculations. So what I do is I look at the frequency response for each capacitor, right? We have the input capacitor, output capacitor of the first stage, input capacitor, output capacitor, bypass capacitor of the second stage, and then input capacitor and output capacitor of the final stage. So looking at all those values, the dominant one is the one that has the highest frequency, which is the second stage bypass capacitor. So that means if I added more farads to that capacitor, it's going to make the frequency response go down. And so now I have 20 microfarads equivalent because I use 2 separate 10 microfarad capacitors. Now I run it, and we can see the frequency response has greatly dropped. And we're at the negative 3 dB cutoff point, and we're getting 58.88 Hertz. And our pass band is still at the 1.23, so it didn't affect it too much. So you might be wondering, okay, like, well, what if I don't want to mess around with that bypass capacitor? Like, what else can I look at? Well, so 40 Hertz, what's the next highest capacitor? We have 8, 5, 25, 32. So maybe the input of the final stage. We'll look at that one. And what I mean by dominant is like, so the output of the third stage wasn't very dominant. So if we added 100 nanofarads to it, we could see how much of a change there is. So let's like cue our negative 3 dB point. So our magnitude's negative 1.77, our frequency is 58.88, so that is our baseline. I added 0.1 microfarads or 100 nanofarads to the output, and let's see what kind of change we get. So it really, we're still at negative 1.77, so it didn't change very much at all. And that's because the output frequency is 5.85 hertz, so it's not dominant at all. The input is 32 hertz, so that's the one that should be dominant. So now let's go back and get it back to our, yep, okay. So now let's add 100 nanofarads or 0.1 microfarads to the input capacitor of the third stage. Let's see how that changes the circuit. Okay, now see how it dropped much more? So now we're at negative 1.76. So then we can decrease the frequency response a little bit, and it went down a little bit. So now we're 58.61. Okay. So that's what I mean by dominant. Okay, so now let's look at, we could look at the input of the second stage. It was 25 hertz. That might be a good candidate. And let's also look at, there's only two capacitors for the input stage, and one is 8 hertz and one is 5.3 hertz. So they're both, pretty close, but the input is going to be more dominant than the output. So if we make sure we run everything back to the way it originally was, just so it's easy to see the change. So the input is 100 nanofarads, which is also the same as 0.1 microfarads. So let's add 500 nanofarads to make it 600 nanofarads or 0.6 microfarads. And let's see how that changes it. Yeah, that dropped it quite a bit. So now we're at 57.9 hertz. So these are the methods that I would use to affect the frequency response, and through simulation it's really easy to kind of just pick and choose what capacitor value you're using, but when you end up building the circuit, there's like, you're going to be having a hard time trying to find a 600 nanofarad capacitor. If you have a whole bunch of capacitors or you buy like a set, there's standard sizes, but also you make sure you're using like a LCR meter and measuring them, because there is a tolerance. And again, if you want a really accurate calculation or an accurate result experimentally, you want to make sure that the capacitors you're using, like what the value really is, not what they say they are, because there's definitely sometimes, 10%, 20% variance in these capacitors. So knowing that, if you're trying to get 600 nanofarads, like you could get a 680 nanofarad capacitor, and you might be able to find one that's like 610 or 620. So you could use that variance for your benefit, but that'll require having a LCR or sometimes digital multimeters you can measure capacitors with. But I hope this helps. This is primarily what I wanted to go over. And again, just looking at this circuit and looking at every single frequency response for every single capacitor, we can tell that the dominant one is the bypass capacitor, the second stage. And then to be able to obtain the pretty accurate result, at least compared to the simulation, what we did is we took the root mean squared of every single stage to get a result, and then we took the root mean squared of all of those results to get a final result. I hope this helps. Thank you.